Okay, in our previous video, we describe product topology using bases. Sometimes it is useful to express product topology in terms of sub basis. So in this video, we're going to study product topology using sub bases. So in order to describe product topology using the sub basis, we need a special type of map which is called the projection map. Now first, let's define the projection map. Projection map. Let's define the projection map, and then after that we will describe product topology in terms of basis. So in order to define the projection map, mm, let's say x and y are my topological spaces. Let's say x and y are the topological spaces. So I'm taking here topological spaces since we want to use our projection map to describe the product topology or to describe the topology. That's why I'm taking x and y are the topological spaces, but is not a mandatory. Those x and y, they have to be topological spaces just to define the projection map. Okay, let's say x and y are two topological spaces, and then let's consider their Cartesian product x cross y. Uh, Here is the graphical representation or visualization of the Cartesian product. Let's say this is our y and this is our x. So this is x and this one is y, and the Cartesian product of x and y is the set of all those order pair here. Now here let's consider the map from this Cartesian product or the set of all those order pair to this set, this topological space X, and let's call that map is pi 1. So here pi 1 is a map from Cartesian product of X cross Y to X defined by pi 1 since x, this pi 1 is the map from this Cartesian product to the first set x. So and then we know the each element in the Cartesian product, they are like this order pair such that x is in the first set and y is in the second set. And let's define this map like this: pi 1 xy is x. Uh, so here we are considering the map from this Cartesian product x cross y to the first set x, which we have denoted by pi 1 and we have defined like this. And also let's consider the another map from the Cartesian product of x cross y, from the Cartesian product of x and y to the second set y, and let's call that map is pi 2, and let's say pi 2 which is the another map from x cross y to the second set y defined by pi 2 xy. Since this map is from this Cartesian product to y, so the most natural way to defining this map is so this guy pi 2 xy takes this order pair to y. Then these two maps, so we have two map from the Cartesian product of x and y to the first set and also to the second set, which are defined pi 1 here and then pi 2 here. And these two maps, they are called the projection map of the or they are basically the projection of the Cartesian product of x and y into the first set onto the first set x and also onto the second set y. And these two map are called the then these two map pi 1 and pi 2 are called the projection are called the projection are called the projection of x cross y onto its first component or first factor and second component or second factor, okay, second factor respectively. These two map pi 1 and pi 2, they are called the projection of x cross y. Pi 1 is called the projection onto the first set, and pi 2 is called the projection onto the second set, which are defined like this. Okay, now here one more thing. So basically this map pi 1, so is a map from here to from this Cartesian product to this set x. So basically now if we pick any arbitrary element x here, right, let's say x, this is an element of this set this topological space x, and you take the the Cartesian product of x with the whole topological space y, you're going to get in this graph or in this figure, this line is gonna be x cross y, and so basically this pi 1, it takes this the whole line to the this point x, okay. That means if we take the inverse image of this element x, that's gonna be this line or this Cartesian product of x with the whole topological space y. So basically this is what is like the x Cartesian product of order pair of x y such that y is in y, okay. So now here you can see that if I take pi 1 inverse of this element x, not the inverse of the whole set x, okay, just the element x is gonna be the set of all those order pair, which is basically x cross y, the Cartesian product of element x with the topological space y. So this is the this is the inverse image of x. So yeah, also we can find the inverse image of any subset of x instead of just the element. Let's say let's consider the open set U. So if we consider the open set U, let me erase this one. Then it's gonna be now when we took the inverse image of element, that's the Cartesian product of x with the whole topological space y. Now here if we take the inverse image of the open set, or simply a set U, is gonna be the Cartesian product of U with the whole topological space. So in this graph, or in this figure, this rectangle or the rectangle that looks like this one is gonna be the inverse. So this is basically the pi 1 inverse U. So maybe you are wondering why I'm talking about this inverse. Basically we're going to describe the subspace topology. We're going to describe the subspace of not the subspace. We're going to describe the subbasis for the product topology on x cross y using those inverse image of the open set. That's why so I'm describing this. I'm giving the visualization of or graphical representation of the inverse image of U. And if U is open, then this inverse image U cross y is obviously open because y is a topological space and U is open. So the Cartesian product of two open set is gonna be open in topological spaces, okay. And similarly now let's take the open set in y, and let me call that guy is V, okay. Then similarly we can find the inverse image of B with respect to pi 2, because pi 2 is the related with y here. So, and if you take the inverse image of B, now what you need to do, you take the Cartesian product of B with the whole topological space y, then it's gonna be like this rectangle here, okay. So this is the inverse image of B, which is X cross B. Now here X is like the whole topological space, and if B is open, then obviously this X cross B is also going to be open. Okay, now so far what we have seen is so we have defined the two projection map, or we have defined the projection of x cross y into the first factor x and also into the second factor using this definition and that one. And then also we have seen that if you take the inverse image of an open set in X, then that's gonna be this Cartesian product, and if we take the inverse image of open set, that inverse image is also going to be open. Similarly, if we take the inverse image of open set B, which is the subset of y, then that inverse image is going to be the Cartesian product of x and b, and that is also open. That is what we have so far. Now I'm going to give a lemma. This lemma, the lemma without proof, and if you are interested in proof, you can take a look in Munker's book. So I'm going to give a lemma without proof, and that lemma, it tells us how to find a subbasis for the product topology on x cross y. Okay, now let's say I have two topological spaces x and y, and also I have two projection map, pi 1 which is defined like this and pi 2 which is defined like that. Then this lemma, it tells you how to find the subbasis for a product topology on x cross y. And here is the statement. Again, I'm not going to prove this this lemma, but if you are interested in proof, you can take a look in Munker's book. Okay, then the collection script as the collection of the inverse images of U such that U is open in X. If you take those, the union of those rectangle which I have highlighted in red, if you take the if you take the collection of those rectangles or rectangular region, not exactly rectangular region, and then take the union of them with this the one that I have highlighted in green. So that's the pi 2 inverse B such that B is open in Y. Now this collection, this union, which is the union of the collection of inverse image of those open set U in X and the inverse image of those open set B in Y. And if you take the union of those collection of the inverse images, then this collection is a subbasis for a topology. Is a subbasis for a topology on x cross y, or you can say is a subbasis for the product topology on x cross y. So this lemma, it tells us how to find the subbasis for the product topology on x cross y. Okay, so basically this collection is the subbasis for the product topology on x cross y. And let me describe this collection a little bit more. Now here pi 1 inverse U, which we have defined here, we have seen here pi 1 inverse U is basically this guy, which is U cross Y, and this one is x cross B. So if you want to find the subbasis for the product topology on x cross y, so what you need to do is you need to find those collection, and also you need to find this collection, and you take the union, right, or you take them together. So here this collection is basically to find the element of this collection. What you need to do is you take the open set in X. Basically open set in X means every element in the topology on X. So you just take the Cartesian product of y with each element of the topology on X. So that will give our first collection. And then the second one is gonna be the second one. So the second collection, to find the second collection, what you need to do is you take the Cartesian product of X with the open set in B. So basically open set in Y, not B. Basically open set in Y, these are the element of the topology on Y. So to find the second collection, what you need to do, you take the Cartesian product of X with each element of the topology on Y. That gives you the second collection. And to find the first collection, you take the Cartesian product of Y with each element of the topology on X. And once you have those two collections, then that's gonna be your sub basis for the product topology on X cross Y. Now let me give you one example. Okay, let's say X is a set AB, or X is a topological space AB with a topology empty set, the whole set X, and this one point set A. So we are here we have taken this set X, or the topological space X with this topology. And now let's consider the another topological space UB with a topology let me call that topology is the empty set. We need the empty set, and then we need the whole set, and then let me take just like this B, this singleton set, or the one point set subset of Y, which is B. All right, now here then by that lemma, the sub basis for a topology, which is basically the product topology on X cross Y, is the collection of. So what you need to do is you take the Cartesian product of each open subset of X with Y. Basically that's the first part in our lemma. And the open subset of X, which are like these three subset of X. So you need to take the Cartesian product of each of them with Y. So let me just say the collection of then the sub basis for a topology on X cross Y is the collection U cross Y, such that U is open set in X, which is one of those three sets, which are phi, X, and A. Is the collection of this one. And the second part in our lemma, which what you need to do is you take the Cartesian product of X with each open subset of Y. In our example, open subset of Y, which are these three sets, because each element of the topology on Y, they are the open set of Y. So let's call that B, and then B is gonna be phi Y, and then this singleton set, this one. So then the sub basis for a topology, or for the product topology on X cross Y, is this collection, this one and that one. Now we can find each collection. So let's find the first collection, which is U. Then that's gonna be your UR. You take the Cartesian product of empty set with Y. If you take the Cartesian product of empty set with Y, that's gonna be Y. and then you take the Cartesian product of x with y, which is this the Cartesian product of x and y, and then you take the Cartesian product of this singleton set with y. Okay, and y is those two elements. Y has those two elements. That means you take the so basically here what you do is you take the Cartesian product of this guy with this one, right? So it's gonna be Cartesian product of this set with y is gonna be the set of order pair a u and a v, right? So just take the Cartesian product of this guy with that set, which is the when you take the Cartesian product, you take the order pair of this one with u and this one with b. So that's my first collection, and the second one is x across b, and b are those three open subset of y. Now when you take the Cartesian product of x with empty set, that's gonna be empty set. Cartesian product of x with y, that's gonna be this guy. Now what you do is you take the Cartesian product of x with b, and then x is this set. So just you take the x has only two elements, which are a and b. So you take the Cartesian product of ab with b. So that's gonna be, when you take the Cartesian product of x with this set, just that is gonna be this set AP, and then Cartesian product of or you take the order pair of B with B, that's gonna be B. Alright, so then the subbasis is basically the subbasis is in the subbasis. Now we just take the collection of, just we write them together, and then the subbasis for the product topology on x cross y is gonna be the empty set you already have here, and then this guy, and then you take a u a b, then a b and then b b. All right, so this is the subbasis. This is the subbasis for the product topology on x cross y. Okay, this is how we find the subbasis for the product topology on x cross y. Okay, that's all for the product topology. So here we describe the product topology using the subbasis. Okay.